Hi everyone, welcome back. In this video, we will talk about Tcache, and we will especially talk about the data structure for Tcache in the heaps. So Tcache is a new notation that introduced since glibc 2.26. The idea is pretty simple. The idea of Tcache is that we want to save some cache of memory inside a thread. And that's why we call it Tcache. It is a thread-based cache. The motivation of having a Tcache in each thread is good because it's going to improve performance. However, the design of Tcache is not as secure as we expect. As a consequence, there are different kinds of vulnerabilities inside the design of Tcache. In our course, we will majorly talk about glibc 2.27. In latest version of glibc, Tcache has been much improved, although there are still vulnerabilities. But for this course, for the idea of conveying you the possible security vulnerabilities and how to attack them, I will still focus on 2.27. So some of the vulnerabilities that I'm going to introduce, they're already patched, but some of them are don't. I'm going to leave it for you to tell which one is patched and which one is don't offline in the class. All right, now let's start. I will start the introduction of Tcache by showing you examples on the right-hand side of my panel. I am using Ubuntu 18.04, which comes with glibc 2.27. In this demo, I'm going to use the program called Gym, which I wrote before our course. And in this program, you will be able to allocate and free the memory. This is just for purpose of presentation. You can always just write the program by yourself, which contains those information. And the reason why I want to write this program and show you is because I want to show you, the process and the heap layout during the time that I allocate and free those memory. Also, I would like to use this demo to show you how to use debugging tools such as PwnDebug to visualize heap layouts. Okay, so now I'm going to start to use PwnDebug to debug Gym. I'm going to use gdb, the command of gdb space /gym, and then now it starts to run. I'm going to run it, and before I allocate any memory, let's first check out the heap. So what I'm going to do is I'm going to use a Control-C to interrupt the current execution. And then I'm going to use this, which is short for this _ heap _ chunks. So now, as you see, it says that there is no heap. And in fact, if you use vmmap to check the current memory layout, you will not be able to find a heap. Now let's continue. Again, those are the current available menu. And then I'm going to use malloc. And then I'm going to say malloc a chunk with a size of 10 bytes. Okay, so now I have allocated a place with 10 bytes. And now let's take a look at the heap again. And also, I am going to interrupt, use Control-C, and then do this, which is short for this heap chunks. So I'll just do this. And now we can see heap. And also, let's check via map. Now we see this new entry, heap. And also, the entry shows over here, heap. Good. Now let's go back to the visualization of heap. So we see something very interesting over here. we know that we only allocate 10 bytes. However, it seems that there's a lot of content over here. Now let's put some content so that we can figure out which part of this visualization belongs to the memory that we just allocate. So what I'm going to do is I'm going to continue and list the manual again. So that is added and the index is 0. And then I'm going to put a bunch of A's over there so that we know where the allocated memory is. Good. All right. So now we found where them. Looks like they are over here because of the bunch of A's that I put. So this part is just to visualize the bytes that I show over here. So for this visualization, these two rows are the actual bytes, and the last column, these two columns are the actual bytes. And then for the last column, it is a visualization for those bytes. Now let's come back to here. So we found that this is actually the parts that correlated with our recent allocation. However, there's still a lot of bytes that are just allocated over here. And turns out those are Tcache. So I show the picture in the slides as well, so that you don't have to take a picture or take a note by yourself, and you will always have the slides later on in the course schedule website. We have a Tcache and we have a chunk that we just allocated. You may wonder where and why we have this Tcache. So don't worry, let's now continue. So I'm going to go back to the demo. Let's free the current allocated location. And now let's just remember what it looks like for the Tcache. So we see that the entire Tcache place, it has a number at the beginning, which is 251. And then after that, the entire Tcache, which is currently colored in blue, it all zeros. Okay, so now I'm gonna continue. And then I'm gonna free this specific allocated memory. So I'm gonna free this. And then let's look at the heap again using this. So now we found that there's something changing in Tcache. And also you can just compare this showing on the right hand side with the picture on the left hand side in the slides. So we found that the difference, there are two parts. One is that there is a 1 over here in the third part of the Tcache. Oh, actually, it's the second part of the Tcache. And the other part is that there seems to be a pointer, because this is exactly some part on this heap. So it looks like there is this part, which is different from here. And in fact, if you take a look at this pointer, it points to over here, right? So the address is this, right? So this pointer ends with 7260 points to the heap at the address of 57260. And now let's take a look at the, And now let's take a look at the freed memory. So what we could do is we can use, actually let me use heap first. So the heap command will give us an overview for all the chunks that has been used or freed. Now we see that in heap, there is a free chunk, the second item, and it says this belongs to Tcache. Related to that, let's use command of Tcache, and we'll be able to see the current information of Tcache. I will explain this in detail later. And also, we can use the command of Tcache beans. And we found that in Tcache bin there is a new item, and with 7260. And if you still remember, that's the memory that we allocated. So we can use the L to list all the allocated memory, which is also the one that we just freed. This is exactly the memory that is recorded in Tcache beans, as well as the item that are recorded by command heap. So now let's analyze Tcache, and also I will explain the content of Tcache in details. For ease of explanation, I already make screenshot from the right hand side, and I'm going to show this in the slides on the left hand side. Tcache is composed of two parts. One is called counts, and the other is entries. And here we see that the content of counts is 1 and then many zeros. And this corresponds to the part over here. The second part of Tcache is called entries. And the entries, as we see over here, right now it's also a list. And the first element of entry is exactly the one that has just freed through our command. So this part is composed of those freed pointers. Actually, it's the bins of the pointers, which I will also explain later. But right now, let's just assume that it points to, it's composed by those pointers that we just freed. Therefore, we can consider Tcache as a big data structure composed of two parts. One is counts, and the other is entries. Each entry of Tcache is also called a Tcache bin. And for each Tcache bin, there are freed chunks with the same size. To help you better understand the data structure of Tcache, let's take a look at the source code of libc. This is the Tcache, and Tcache is in the type of Tcache per thread struct, which is here. So according to the definition of the struct Tcache per thread struct, we see that there are two parts. One is counts, and the other is a list. So the count is the number of chunks that are available for each bins. And Tcache entry star entries is all the entries that has been recorded. And those entries, as I mentioned, this is what is called a Tcache bin. And inside each of the Tcache bin, it will composed of all the chunks with the same size. And those are chunks that are already freed from the use of the program. And here for Tcache bins, let's look up. The value of Tcache max bins is 64. We can also understand how each Tcache bin stores a lot of chunks by looking at the source code. Let's take a look at the struct of Tcache entry, which is right over here. If you look at that, you will find that Tcache entry is pretty simple. It has only one argument inside the struct, which is next. Essentially, this means that a Tcache bin, or say a Tcache entry struct, is a chain. And inside this chain, Each element will point to the next element. Now let's map the argument in the source code to the actual heap layout. Recall that there are two variables in the data structure of Tcache, counts and Tcache entries. So counts is 64 bytes. And then entries is 8 bytes for each pointer times 64. And then there is another part, which is to start to represent the size of the entire Tcache, as well as a padding in the end, plus this 216. So that's going to be 64 plus 8 times 64, and then plus 16 again, which is hex 250. That is exactly this part. And later I want to talk about chunk. I will mention the metadata in each chunk, and you will be able to understand that this particular field actually represents the size of the allocated chunk. Now let's continue with our demo. I'm going to create a new demo, but still using the gem that I coded. So I'm going to run again. And then in this time, I'm going to be first allocating 3 memory. But differently, the third one that I'm going to allocate is going to be different from the first two in terms of size. Now let me list them all. And then next, free them one by one. Remember that I am freeing them in the order of the way that we create them. So I'm going to free the first one, which is F0, and then the second one, F1, and then F2. Now I'm going to interrupt it. And then let's look at the heap. We see that after we free these 3 parts of memory, in the Tcache, there are 2 bins has been filled. And then for this bin, it's going to point to the address ended with 7280, which is here, the second bin with the size of hex 20. And then the other one points to the solely bin with the size of hex 30. If we look at the second bin of size hex 20, we also found that this part is the address of the first bin. And this is exactly how chunks inside the bin gonna connect together and compose the entire bin. So glibc uses a chain data structure that lists all those chunks with the same size together. And then inside the Tcache bin, in this way, it only needs to remember the first bin, starting from which you will be able to get the rest of the chunks within the same size. Now let's abstract the data structure into diagrams, and hopefully this will help you to have an intuitive understanding for what's going on of Tcache. Tcache is composed of 2 parts, counts and entries. Each entry is also called a Tcache bin. In Tcache, freed chunks with the same size will be stored together. And then in the Tcache entry, it will store the first element of the chunk chain. Starting from there, we'll be able to get the rest of the chunk, and as well as the size using the counts. Tcache improves the performance of memory management in the way that every thread will be able to manage a part of the memory as a cache so that it doesn't have to recycle or clean up this part of the memory once it is freed or it's reused again. However, we cannot have a lot of space for Tcache in each thread because it's gonna occupy a memory. And there is always a balance between the size of the memory, as well as the performance. Therefore, in design, Tcache has only 64 entries. And also for each Tcache bin, the chain of the Tcache chunks with the same size will only have 7 chunks at most. In our future videos, I will talk about the scenario when Tcache is full. And in such case, when Tcache is full, the free chunks will go to other bins. Chunk is the memory that is going to store the data that we'll put into an allocated place. So when we do malloc in C, we will be able to get an address back from alloc. In reality, the actual allocated memory is going to be larger than what we require. And this is because for each memory chunk, when it is allocated per design of ptmalloc, or actually I should say dlmalloc, I will put metadata into the allocated chunk. For example, if we allocate a memory with the size of, say, 10 bytes, then I'll extend that to hex 20, which is 32 bytes. In this 32-byte memory chunk, the first 8 bytes is regarding the size and flags of the particular chunk. And this is what we said metadata. For example, if you look at the purple memory chunk over here, this part, which is the first 8 byte of the chunk, represent the chunk size as well as flags. Flags is only 3 bits. So that means that we don't need to look at this part. And then chunk size over here is hex 20. And this is also part of the reason why memory, when it's allocated, it has to be aligned with 16 bytes. This is because the last part of the metadata will be used for flags. And also, for allocated chunk, the minimum size is hex 20. Even though you are doing malloc 0, you will still get a chunk with a size of hex 20. The layout of the chunk when it is allocated and when it is freed are different. The difference is that when a chunk is freed, there will be a pointer stored in the freed chunk. This is because in Tcache, when a chunk is freed and put into Tcache, it will be in part of the chain. So in order to be in the chain, the freed chunk has to point to the next place. Therefore, a forward pointer is necessary for a freed chunk, and usually the forward pointer will be stored right after the metadata. Now I'm going to run the demo again and demonstrate the freed and allocated chunks. So I'm running the program, and this time I am going to malloc 2 chunks with the same size. And then I'm going to free them. But actually for the second one, before I free them, let me put some content over there. Now let's use this command again to check the heap layout. And we found that for the second chunk that is freed, it has stored the data, which is the pointer that points to the first free one. And then if you look at here, you know that originally this entire place is full of A, which is 61, and to this byte. And then when the chunk is freed, the first part of the chunk will be overwritten by the pointer, which will point to the first freed chunk with the same size. When freeing a chunk, glibc will first check Tcache and see if Tcache bins still has place for this chunk with the same size. If Tcache bins has space, the free chunk will go to Tcache bin, and also it will add this Tcache to the head of the chain. Similarly, for memory allocation, also glibc will first check if there is any chunks available in the Tcache bin. And if there is, then glibc will use the available chunk from Tcache bin directly. You may wonder why we always want to use the first Tcache bin, or say put the free chunk into the first. This is a little bit like stack. It is first in and then last out. The reason is that Tcache's goal is to get a good performance. So when we insert a new element into a data structure, using list and then appending to the head of the list is the fastest way to go. If we're going to append it to the end of the list, we have to go over all the elements in the entire list so that we will be able to get to the end and then append the current element into the end. However, if we just insert the element at the head of the entire list, all we need to do is to write the value of the current header as part of the data value into the releasing chunk. The releasing chunk will become the new header. And then we just need to update the entry in Tcache bin so that we know where the new header is. So far, we have talked about the data structure of Tcache. When Tcache is designed, it's designed in the purpose of high performance. However, there's not too much consideration in security, and this is why Tcache was very vulnerable when it was firstly created. In the version of 2.27, there are still a bunch of vulnerabilities regarding Tcache. In the next video, I will start to introduce to you different kinds of Tcache related vulnerabilities.